So the control flow in such a system looks like this. So suppose you have the C code, which is basically if x equals y, then do some code B, else do some code C, and then finally do code D. And if you draw a control flow graph, then you basically have code A, which does something, and then you have if x equal y, and then you have the branching. If true, you go there. If false, you go there, and then finally you do D, whatever D is. As assembly code, you would basically have it looking like that. So you have the code for A, then you have the if statement, and then there is a go-to statement that basically puts you, if true, if x equals y, you go to code B, but if not, then you continue on this, and then you go to, at the end of code C, you go to code D to start implementing this. And if you remember the likely and unlikely keywords that were used in Linux and that we have talked about earlier, this is basically what likely does. What likely does is that it tries to tell the compiler that if you have likely here, if you have a directive that says likely here, if likely x equals y, then you basically would most often jump to this part of the code, and then you can start prefetching, and we'll talk about this in a few seconds, or sorry, a few minutes. And the instructions should be programmer invisible state, should have programmer invisible state to optimize the speed of instruction execution. And to do that, you basically have one of two choices. The first one is that you're in state A and you're going to state B through some transformation, and that transformation can be the addition. I mean, it's your program basically. And let's talk about something like addition, for example. Then one way is basically to have a condition that to transfer from first state to the second state, you must do that in a single clock. That basically means that the fastest your processor can be is the slowest can only be as slow as your slowest instruction that you're trying to implement. So single clock cycle processors are processors where anything will always take one clock cycle, and then the processor cannot go faster than that, because clocks are hardware that you build your computer with these, and you cannot change them. So you basically have to take the slowest command, the slowest operation to be your guideline here when designing your processor. On the other hand, there is a multiple clock cycle processor where you can basically do this part in one clock cycle, do the second part in one clock cycle, do the third part in a third clock cycle, and then you end up at the end result. So if this is, for example, an addition operation, then in this case you would need to have, if you have like load in the beginning, so if you add A plus B and store it in C, for example, then this is actually four things that you need to do. So you need to load A, load B, add, and then store. So these are four things that you're actually doing when you're doing the adding, and you basically have to go as slow as this. Versus if you go for choice 2, I mean, your processor has to be as slow as this if going for a single clock cycle processor. While in the second one, you can have the fastest clock that you can ever have, that physics can give you basically, and divide the same instruction on multiple clocks. So one instruction can take 4 clocks, 5 clocks, 8 clocks, 20 clocks, we don't care. And this is how you can implement something like an FFT and not care about it, because it's not going to bring your whole processor to be slow, but it's just something that affects itself.